Hi, welcome to the solution video for the 22nd STEP Support Programme Foundation assignment, where we're sketching graphs. And actually I remember a couple of years ago when I imagine in your position, seeing this question and being completely baffled, as it does seem very hard to tackle. It's not an equation I'd seen before, but actually there's a few steps you can take just with any graph sketching question that will pretty much turn them all into the same kind of ordeal, at least at step level. So actually I've made a checklist here. So axis intercepts, the first thing to look for, stationary points, and the behaviour as the graph approaches plus or minus infinity in the x direction. So let's just start by going and finding some of these so we can sketch this graph. So let's start with axis intercepts. So that's y-intercepts and roots. So let's start with x is equal to 0. So that's a y-intercept. And so, yeah, we're going to be setting x equal to 0, which gives e to the x is equal to 1, and the value in brackets as 2. So is equal to e to the 0, 2, which is equal to 2, because e to the 0 is 1. That means that 0 and 2 is a point on the graph. And actually, I think it's worth just putting as many of these on the graph as soon as possible. So I'm just going to draw some axes very quickly and mark this point on the graph. So 0 in the x, 2 in the y. Just so I don't have to scroll back and check the information again, so it's all there in one place. That helps me just kind of stay on top of things while graph sketching. Okay, now let's go for y, for the roots, sorry. So we set y equals 0. And this means that 0 is equal to e to the x, just the right hand side saying exactly the same. I think it was 2x squared minus 5x plus 2, I think. Yes, it was, good. Let's solve for x here. So either e to the x is equal to 0 or 2x squared minus 5x plus 2 is equal to 0. Let's deal with the e to the x is equal to 0 first. This implies that ln of 0 is equal to x, just lunning both sides. But ln of 0 doesn't exist, that's not defined, because we have the number here has to be greater than 0. So we can just ignore this outcome, that bit's never going to equal 0. But we can still have the expression in brackets equaling 0. So I think we might be able to factorise this. So I'm going to try to do it by inspection. So let's see, we want two numbers that add to 2, so let's maybe try minus 2 minus 1, I think works, and yeah, it does. If you wanted to do this with the quadratic formula or completing the square, that's completely fine. I think it's quite a useful skill to learn, being able to factorise stuff like this just by inspecting it, but of course, by no means necessary for STEP. It wouldn't take much longer to use the quadratic formula or something along those lines. So anyway, back to the question. This implies that x is equal to 1 over 2 or x is equal to 2. So this gives our roots as being, or the coordinates of these as being 1/2, 0 and 2, 0. So these both lie on the graph, so let's also add those to our diagram. So we have, and also I should add numbers as well, that's very important. 1/2 and 2. Perfect. So okay, already done with axis intercepts, that's great. Now for stationary points. So we want to differentiate our curve's equation, and we want to set it equal to 0 to find the x location of these. And actually you might have noticed that missing from my checklist is the nature of stationary points. And actually sometimes, oh, that's not what I wanted. Sometimes the equation, you might have to find the nature of the stationary points, but actually I think we can avoid it here. and just kind of put the points on our graph and use the other information we have about the graph to find what their nature is going to be. There we go. I've copied the equation again. So yeah, we just need the coordinates of the points in short. So let's find dy over dx is equal to, well, using product rule, we have e to the x 2x squared minus 5x plus 2, because the derivative of e to the x is e to the x, plus e to the x, 4x minus 5. And we can factorise this to get e to the x 2x squared minus 5x plus 4x is minus x, minus 5 plus 2 is minus 3. Okay, so now we want to see when this equals 0 to find when it's stationary points. So dy over dx is equal to 0 implies that 0 is equal to e to the x 2x squared minus x minus 3. And very similarly to last time when we were finding the roots, we can either have e to the x is equal to 0, which we know isn't possible, or 2x squared minus x minus 3 is equal to 0. So again, let's try to factorise this. 2x, and we have an x here, and so we want, let's say minus 3 plus 1, I think works. Yep, that does, is equal to 0. So this means that we either have 2x minus 3 is equal to 0, so that is x is equal to 3 over 2, or x plus 1 is equal to 0, i.e. x is equal to minus 1. Okay, so these are both the locations of our stationary points, but of course we need to find their y values as well, so that we can actually mark them on the graph. It's no use just knowing their x values here. So let's substitute these x values back into the initial equation for y, which again I think I'll just copy. There we go. Cut off a bit, but I think that's okay. So let's substitute x is equal to 3 over 2, which implies that y is equal to e to the 3 over 2. 2 to the 3 over 2 squared is 9 over 4 minus 5 dot 3 over 2 plus 2, which is equal to, a bit messy, but oh well, e to the 3 over 2, and what is that? That's 9 over 2 minus 15 over 2, so that is minus 6 over 2 plus 2, so it doesn't come out too horribly, is equal to minus e to the 3 over 2. Okay, so we have a stationary point at, what's the x, 3 over 2, and the y is minus e to the 3 over 2. Perfect. Okay, now let's solve for the other points where x is equal to minus 1. So x is equal to minus 1. I'm wanting to copy down the equation again, but we'll see if I can just do it by memory. I can't. There we go. E to the minus x, and then I think we have a 2x squared minus 1 squared minus 5x and plus 2. Just check that's right, that is. Okay, let's simplify this, which is equal to e to the minus, oh, and also, sorry, didn't substitute in the value for minus x here. That's just in e. So, okay, e, open brackets, 2 plus 5 plus 2, which is 9e. Perfect. So, we have a stationary point at minus 1, 9e. Cool, so let's add those to our graph. And it's worth noting, and you actually should probably state this as well, that e to the x is positive for every actually for all x. So that means that this stationary point here lies above the x-axis, because 9e, well, e is e to the 1, which is positive, and this stationary point here lies below the x-axis because the y value is negative. It's minus a positive value. Okay, so let's mark those on. So we have minus 1, 9e is one of them. So that's going to look something like this. And the other one is, and of course it doesn't have to be exactly to scale, like obviously 9e is quite a bit bigger than 2, but I can't fit it on the graph. I'm going to make the most of it, and I can always copy it down quickly at the end to fix the scale if I need to. And we also have 3 over 2 minus e to the 3 over 2. So that's 3 over 2 minus e to the 3 over 2. So that is about here. And you can already see that it may not be helpful to know whether this is like a minimum point or a maximum point, because the graph has to come this way anyway. I suppose you could make a case for it coming like this, but then we'd need stationary points at these two, which we didn't find was the case. We found just 2 stationary points. So there's a lot that you can deduce from what we've already found. So, okay, we've done the stationary points. Now we just need behaviour as x approaches plus minus infinity, which luckily doesn't take too long. So let's do that down here. Got the equation here again. So let's first consider, just go back to paintbrush, sorry. So as x approaches infinity, well, we have e to the x approaches infinity, and this value in brackets also approaches infinity. So y approaches infinity. Okay, so that means we know that as we go to the kind of right side of the graph is going to go upwards into the kind of top right quadrants. And so as x approaches negative infinity, we have, well, e to the x approaches infinity, but this kind of polynomial here actually might approach negative infinity, might approach positive infinity. We're not that sure. But if you read the question, and I've maybe underlined this just so I'd remember about it, you may assume that x to the n e to the x approaches 0 as x approaches minus infinity, which of course would have come up because they put it here, and this is where we're using it. So in fact I'd be a bit worried if I reached the end of the question, reread it, and I hadn't used it yet. So it's good we're using it now. For any integer n letters as well. So let's quote that down here. So notes that e to the x multiplied by 2x squared minus 5x plus 2 equals e to the x multiplied by 2x squared minus e to the x multiplied by 5x plus 2e to the x, which approaches 0 by maybe we should say as stated in the question. As we go really far to the left of the graph, we're going to be reaching kind of the x-axis. So we're going to have some kind of asymptote behaviour going on there. Okay, let's now sketch this on the graph. So I think we're ready to kind of just join the dots at this point. We've got it kind of going really big here. We've found everything that we could have. There's not going to be any magical stationary points or roots or y-intercepts that are just going to appear. So let's just join it up. We've got to go through this too. And actually this is why I'll probably redraw it after this, but I'm just going to undo that and make it a bit steeper. It does take a couple of tries, which is why I really recommend you do it in pencil, We need to reach this turning point, or the stationary point. It's going to be a turning point here because we need to get back up to this 1/2. Now we need to get through this 2. We need to be ready to have a stationary point at this one here. And now we need to be ready to asymptote to the x-axis. Note we can't cross the x-axis because we've got no more roots, so we've just got to be like this. And I think it's quite satisfying to see that everything we found earlier plays into determining the graph. So if we were missing any of those bits of information, the graph would either be different or we just wouldn't have enough information to find it. But that was as much as we needed. We didn't need to take any second derivatives or anything. If you did, that's completely fine. So you might want to reassure yourself by taking a second derivative and checking how that that it corresponds with what you've drawn. But what we did is completely fine here, and it will work for the majority of graph sketching questions. So okay, now we get to like kind of the beefy bit, I think. So hence determine how many real values of x satisfy this equation equals k. So this is kind of exactly the same as what we had up here, but with a y instead of the k, in the different cases that arise for the value of k. So I think it's worth thinking of how we can visualise this. So we're effectively setting our curve here equal to y is equal to k. So we're seeing how many intersections are there between these two curves. So that might be similar to, say, setting y equals x and, I don't know, y is equal to x squared equal, to see like how many intersections they have with each other. We're doing the exact same thing here, just with a bit more complicated of a question. So, okay, let's draw a line and see what it looks like. If this is, and I might just give it a different colour. There we go. If this is y is equal to k, let's say for some like lowish value, then we're going to have no intersections. So there's going to be no real values of x that satisfy this. And I'm just going to slowly move it up. I think you could potentially do this in your head or draw it out with some ruler lines, and then we'll write it down afterwards. Here we've got one intersection. So this is where this is where the y value, so k, is equal to minus e to the 3/2. And as soon as we're away from that, we get 2. So we've got 2 intersections here, 2 real values of x satisfy this equation. And until we get greater than this value y equals 0. Note at y equals 0, there's only 2 intersections still. We're not hitting that asymptote yet because the asymptote never reaches. So what I'm trying to say is that this kind of bit of the graph that approaches 0, it never actually touches 0. But as soon as we get above 0, we now have, if it will let me move it, oh, might have to draw a new line. We now have 3 intersections. So we're going to keep moving it up. 3 intersections, 3 intersections, 3 intersections, 2 as soon as we hit this turning point here. And as soon as we get away from it, this is just at one point there are 2 intersections, there's now 1 solution. And of course the graph approaches infinity, so we can go as high as we want and there's only 1 solution. So that's one way to view it, but again, you can, if you want, just like draw it on with a ruler, but it's definitely, you're meant to be doing this graphically, which is kind of hinted at by you having just had sketched the curve. So the parts aren't irrelevant. Make sure you definitely make use of it. So okay, now let's write it down. It's not enough to just kind of say it verbally, is it? I think I'm going to copy my graph and then we can do it at the bottom of the page. Scroll all the way down. Here we go. So for y, or even for, I'll flip back to blue. For k is less than, sorry, that's a less than sign, is less than minus e to the 3/2, 0 intersection. So it's like 0 values of x. And if you remember, that was right at the bottom when we had a line like this. Any of these don't intersect at all, so there's no values of k, no values of y, for which this is the case. Now at k equals minus e to the 3 over 2, we have one value of x. And that's where we intersect exactly here. If we're a little bit below, there's no intersections. If we're a little bit above, there's one intersection. So that's why there's just the equals. Now, okay, if we have 0 is less than or equal to k is less than e to the minus e to the 3 over 2, then we have two values. So that represents any region kind of here, where we can be on the 0 line, because the asymptote doesn't, like this bit of the graph, doesn't touch 0. It just approaches 0. And we can't be here. So that's shown by the strict and non-strict inequalities. Okay, now we have three values as soon as we get above 0. So we have 0 is less than k is less than 9e. That's three values. So that's for stuff like here. And then as soon as we get to this turning point here, there's two values again. So this is just an instantaneous point. We just have an equals sign. 9e. Yes, k equals 9e. We have two values. And finally, almost there, we've got k is greater than 9e, gives us one value. And those are values of x which solve this equation. And we're done with the first part. Oh, and sorry, I'm aware you might not have been able to see these ones at the right. There you go. Okay, let's now move on to the next part, where we're sketching another curve. And we've already spent probably more than 15 minutes at this point doing the first part of the question. We don't really want to be spending much longer than half an hour on this, in an ideal scenario. But luckily we don't have to be just sketching it all over again. We can use a little bit of information from the first part to help us in typical step fashion. So let's just go back to both parts. What kind of similarities are there between these two? And if you haven't noticed yet, I'd maybe recommend pausing the video and just seeing if you can see any kind of similarity between these two equations. And yeah, we've replaced all of the x's with x squareds. So x to the 4 is equal to x squared squared. And yeah, the same for that. So yeah, this is where we might view I as f of x. I would be f of x squared. And actually something that comes up quite a lot in STEP that's definitely helpful to be familiar with is if you know f of x, how can you sketch f of x squared? And how can you sketch f of x all in brackets squared? They are different. And if you want, it might be worth pausing the video and having a think about how you deal with them. So okay, let's go to this question. This is kind of same as I, but with x squared rather than x. We're replacing kind of this x-axis with an x squared now. So where we might have had, I'll go back to our graph here, where we might have had 2 as being the root here, now root 2 is the root, because we're squaring everything in the x direction, but the y's stay exactly the same. Another thing that's worth noting is that this function is now even in the x direction. So for example, if I take f of minus x, it's now equal to f of x, because we're squaring both of these. If we take minus x here, and I'll show that to you actually. Let's do that here. Y is equal to e to the minus x squared. So this is just replacing x with minus x. 2 minus x to the 4 minus 5 minus x squared plus 2, which equals e to the x squared to x to the 4 minus 5x squared plus 2. Exactly the same as the equation for positive x. So it needs to be symmetrical in the y-axis on new graph, is what I'm trying to say. And any kind of, in our old graph, anything that was over here, we're going to want to ignore pretty much and just reflect everything that was here. Okay, and pretty much otherwise we can kind of copy down what's going on in this graph. So let's give it a go. So last time, I won't do anything too specific yet, we had something along the lines of this. Oh, whoops. Not the best graph I've drawn. And now we're replacing the x with an x squared, so we get something along the lines of actually, I think I should probably redraw that first one now I think about it. So yeah, last time we had this, that's a bit better. And yeah, now we're replacing the x with an x squared. We'll have something like this, and then it's going to be smooth still, because kind of stuff closer to the y-axis is going to be spread out a bit, and stuff further away is going to be squished in. You can think about that a bit if you're not immediately convinced by that. Yeah, this is going to be more or less the shape of the graph. So now let's try to draw it on its own graph and label some values. So we've got something like this. Just from our previous graph. And remember, the y values aren't changing and the x values are just being square rooted. So we have a 2 here, so let's square root it, and it's so important that you fill the values in. There are definitely marks for that. So we have a square root of 2 there. And remember, we're just reflecting in the y-axis. This is minus root 2. We have a half is the other root, so this is 1 over root 2. And this is minus 1 over root 2. What else? We just have the turning points. The y values are exactly the same, and we square root the 3 over 2. So square root of 3 over square root of 2. And the y value, I think, was, I can't remember, minus e to the 3 over 2. And we have the same here, minus root 3 over root 2, and minus e to the 3 over 2. And actually, we've got one more point that's worth labelling. So we want to label all the turning points and the points of intersection with axes. We want to label this point here, which we can tell is x is equal to 0. And that would be the only place it's made sense to arise. And now where would the y value be? Well, that's just the y-intercept, which we already found as 2. So we have a 2 here. And we're done with this graph. So I know it seems, and I probably should have used a ruler, sorry for those axes. I know it seems like quite daunting looking at this question, but actually we've done all of the work already. There's really just a small transformation we need to do, which once you've done a couple of times should become like kind of second nature. And then we just need to sketch it. And that's the end of the question. I hope you'll appreciate that the curve sketching questions, they can be very difficult at first, but once you've learnt the technique, they are all very similar. So it's definitely worth spending some time on, especially for finding it a bit hard now, and it will get a lot easier with time.